A fisherman's job can be very dangerous, making communication at sea crucial in times of emergency. With the use of M-Fisheries mobile application, fishermen can communicate during emergency situations. However, cellular coverage at sea is very limited. To expand the coverage at Mayaro, Trinidad, our design aims to achieve the maximum link length using Wi-Fi 802.11a router on-board to router on-board technology. The marine environment is an open space with little or no absorption to wireless communication. Factors which can affect radio wave propagation in the environment are water surface reflection, wave rocking motion which creates unstable signal reception, the Earth's curvature which becomes an obstruction at large distances, and atmospheric conditions which can lead to ionosphere delayer absorption for frequencies less than 7 MHz. We have investigated and analyzed various propagation models to determine which would be most suitable for our application. Factors which motivate our choice were propagation loss, rain attenuation, signal blockage, antenna height, power of transmitter/receiver, operating frequency, distance between transmitter base and receiver, and the bandwidth. It was determined that the ITU RP.1546 model was the most suitable model because it is applicable in sea environments and also incorporates factors such as reflection, refraction, diffraction, and scattering among those previously mentioned. Compared to the free space path loss, also accounts for field strength and can be used in longer distances by increasing the field strength or frequency. The link length is determined by the quality and quantity requirements of the link. The quality metrics include high signal to noise ratio, low bit error rate, low delay, high reliability, and low jitter, while the quantity metrics include throughput and bandwidth. Given the specifications seen, various calculations were done to determine the maximum link length due to free space path loss, SNR, and the Earth's curvature. Firstly, the link budget equation, equation 1, which includes receiver and transmitter power, antenna gains, and other losses, was used to determine the free space path loss. Then transposing equation 2 for distance in kilometers and frequency in megahertz, the maximum link length was found. When calculating the distance due to SNR, a new receiver power was calculated using equation 4. After determining the minimum SNR for the router and noise power given the bandwidth, temperature, and Boltzmann constant as seen in equation 3. The calculations as done for maximum link length due to free space path loss were repeated using the new receiver power. For the Earth's curvature, the distances to the radio horizon from both the transmitting and receiver antenna calculated using equation 5 are summed to give the maximum link length. The distances due to free space path loss, SNR, and the Earth's curvature were found to be 8.21 kilometers, 11.27 kilometers, 22.58 kilometers respectively. The distance obtained from the simulation was found as 14.02 kilometers. The maximum link length was determined by most limiting factor. In this case, it was the free space path loss. Using the Shannon-Hartley theorem, the channel capacity was found. The difference in the theoretical and simulated values was because the simulation used a different value of receiver sensitivity. The radio mobile simulation software uses irregular terrain model, which can account for the differences between the theoretical and simulated values, as the software may have used calculations based on the Longy-Rice model. One recommendation for our application is to increase the signal power of the router, which will in turn increase the SNR and thus the distance.